Oxidation of alkene, we can do it in a few ways. Step 1, epoxide formation. Recall the 3-member ring that includes the oxygen. We need something called the MCPBA, stands for metachloropyroxybenzoic acid. Small m, capital C PBA. Using dichloromethane as a solvent, you get the epoxide from the double bond. And take note that epoxide, right, because you need to have 3-member ring, so these new bonds here must be from the same side. So again, it is like a syn attack. And this is the byproduct. For hydroxylation, we use osmium tetroxide, call it osmium tetroxide, or osmium 8 oxide. Both are fine, okay? And again, you have a syn addition, because you see the newly created bonds are from the same side. This is an intermediate, a cyclic osmate intermediate. Subsequently, you added this reducing agent, which is sodium hydrogen sulfide. You get the cis 1,2-dimethyl cyclopentane 1,2-diol. So the diol will be cis. The last one, ozonolysis. Ozone from the ozone layer, O3. Where do you find ozone? You can find it at home. You know the printer, where you print out many sheets of paper, black and white, all that. Then you take this fresh paper and then you smell it. That smell is ozone. Very bad for you, strong oxidant, bad for health. So if you have anybody working in photocopying shops, you should let them know that this is harmful and they should take breaks from time to time. Alkenes with ozone, under these conditions, you first get this intermediate called molozonite, cool name, huh? And then finally it will rearrange itself. It is a spontaneous reaction, you don't need any catalyst. You form an ozonite, and then in the presence of zinc, you need this. Because it is a reducing agent, they can cut the bond off and you get 2 carbonyl compounds here. Okay? Recall that using OSO4, pyridine is a solvent. Using OSO4, you must get a cis isomer of the alcohol, right? Direct oxidation, one-step mechanism, syn addition, stereochemistry. Super important. Using epoxide. Once you found the epoxide, you add the acid. It will open up. What do you see here? You get a trans diol. So here we're trying to illustrate to you the example. Depending on cis or trans diol that we want, we use different reagents. You have to know this. It is supremely vital to your exam. Here, like I just mentioned, what happens here is you have a zinc in the last step, cutting off the ozonite. You get these 2 parts. Now let's try this example. You have this funny looking alkene here. You put O3 and zinc. What you got to know is, right, you just cut this up, pull it apart, and insert the O on each side. You get 2 fragments. That's all. Very simple. 2 ketones. Next one, same thing. You identify the carbon-carbon double bond. You just do this, cut, pull it open, and then insert OO, and you're done. Now alkynes behave similarly to alkenes, but like I said before, it is less reactive than alkenes. So various reactions can often be stopped at the mono addition stage if 1 molar equivalent of reagents used. So for hex 1-ine, we add just 1 molar equivalent of HBr, that means it's 1:1 ratio, which is only enough to form this, the alkene form. But now when we spam excess, you can continue to react to form the 2,2-dibromohexane. HCl, again similar. Here you get a Z 3-chlorohexene. Recall how do you determine whether Z or E? Go back and revise your lecture notes. This is the product. For the Br2 addition, Recall that Br is big enough to form a 3-member ring, a bromonium ion. So here again, realize that this is an anti-addition. You get the E alkene isomer. You spam a lot of Br2, you get the 1122 tetrabromobutane. Hydrogen, recall, linear catalyst is also a form of heterogeneous catalyst because it's also a solid. So the HH must come from the same side. It is a syn addition. Okay, so these newly created bonds must come from one direction. More hydrogen, you get octane. For terminal alkynes, they are relatively acidic. Important to note this. And this reacts with a strong base such as sodium amide. Terminal hydrogen is removed, forming an acetylide anion. Now, how do you explain to someone that this molecule is acidic? An acid will give off H+ and a conjugate base. If the conjugate base is stable, then the molecule itself is acidic. So it means that in this case, your acetylene anion is stable. But why is it stable? Remember that carbon is not that electronegative, but it's also not that electropositive. So why in this case it prefers to take the negative charge? The reason goes back to your orbital theory. Here, carbon is having a sp hybridization, which means that it has got 50% s character and 50% p character. P means you have a p orbital character that's more diffused. S means you have a sphere that's very close to the nucleus. When we have a negative charge and with more s character, it's held more tightly by the nucleus, so it can stabilize it. Okay, so this anion here, because it's having a lone pair of electrons, it can act as a base, conjugate base, as a nucleophile. Now let me use this as a nucleophile to illustrate to you what happens. Nucleophilic substitution. An acetylide anion will attack a carbon that's delta positive because it's being polarized by the bromine, kick out the Br, and you join it to form propyne. Hex-1I, first you throw in a strong base, sodium amide in the presence of a solvent, ammonia. Then you kick out this one and you take this carbon and attack this carbon here, joining the Br, you elongate the chain, tada, Dec5-ine. So this is how you build up your carbon chain in the molecule. That's all for today. See you.